All right, great. Welcome everyone to our space webinar series. We had a brief hiatus for um, for a little bit, and then we are back now with a talk by Professor John Wright. And let me give a very brief introduction. John is an associate professor of electrical engineering at Columbia University. He's also affiliated with the Department of Applied Physics and Applied Mathematics at Columbia's Data Science Institute. He received his PhD in electrical engineering from the University of Illinois at Urbana-Champaign in 2009. And before joining Columbia, he was with Microsoft Research Asia from 2009 to 2011. His research interests include sparse and low-dimensional models for high-dimensional data, optimization, and applications in imaging and vision. And his work has received a number of awards and honors, including the 2012 Colt Best Paper Award and the 2015 PAMI TC Young Researcher Award. And his talk today would be on geometry and symmetry in some non-convex optimization problems. And without further ado, let's welcome John again, and I look forward to his wonderful talk.
Okay, great. So thank you, Sai, for the introduction, and thank you to all of the organizers for the invitation. It's wonderful to be here in space, as we so often are these days. And hello to everyone. I see a lot of familiar names in the participants list, so it's great to see all of you virtually. So what I'm going to do for today's talk is to talk a little bit about non-convex optimization from the perspective of symmetry. So talk about some adventures that my students and I and others in the field have had over the past few years in trying to identify non-convex problems that we can solve in a strong sense. It's going to turn out that at least for the classes of problems that we understand, there's this really beautiful role of symmetry to play in describing when and why you can solve problems, sometimes to global optimality. So that's the theme of the talk. As Sai said in the chat, you can feel free to ask questions. I think it's actually fun to have a little bit of back and forth during the talk, especially in this virtual setting. So feel free to put something in the chat, raise a hand, even unmute the mic, and we can see where we get to. So before I go into some of the technical stuff, I'll just thank my collaborators. The main theoretical results that you'll see today are joint with Yuqian Zhang, Qing Chu, Henry Kuo, and many others, and the experimental results, there are a lot of folks here and who I'll thank later who contributed. Okay, so this is, I guess, a webinar series on computational imaging, as I understand it. And so I probably don't have to tell you why optimization is important, right? Optimization is a sort of fundamental technology that's underlying a lot of interesting things that are happening in this area and in science and engineering in general. Of course, the canonical examples that one gives of these types of things, this type of development is in large-scale machine learning, where we're solving enormous optimization problems to train very complicated models on very large data sets. This is having an impact that really can't be overstated on the way that people solve problems, both in imaging, in computer vision, in related areas. And of course, this is not the only place that optimization is useful. There are many places in computational sensing, in imaging, in signal processing in general, where we solve optimization problems in order to reconstruct or interpret sensed data. So optimization is a really important workhorse. And so, what is optimization? Well, probably everyone who's on this call knows this and solves optimization problems every day, right? We have an objective function f of x, and we're trying to make f of x small. And of course, we know that the geometry of F plays a really big role in determining whether we can be successful at this activity, right? It's easy to construct F that are easy to optimize. It's also easy to construct F that are very hard to optimize. So in the example at left, of course, the objective function is this nice bowl-shaped thing. And so no matter where I start, I'm going to be able to use local information to sort of ski down to the bottom and find a global minimizer. Whereas at Wright, maybe this is a little bit harder, right? At Wright, local information is not very indicative of global structure. And so, in general, we're in trouble. And I think this distinction between easy and hard problems is one that, we as sort of signal processors or people who work on machine learning related areas sort of always have to have at the back of our head. In contrast to classical applications of optimization, think about, say, a portfolio optimization problem or something in logistics where your goal is maybe to maximize an expected rate of return. There, local improvements are very meaningful, right? If I locally improve my portfolio, well, hopefully I'm making more money or something. Maybe the goal is not that, but local improvements are meaningful. But here, when we come to machine learning or computational imaging, we really don't care about optimization per se, right? Optimization is only a device to get us an answer. And what we really care about is the quality of that answer. Maybe we want to know whether our classifier will generalize to unseen examples. Maybe we want to know whether the image we reconstruct will actually correspond to the physical ground truth that's out in the world or inside our body, right? And optimization is just a device to get us there. And so we sort of have a stronger or higher bar if we're really serious about the quality of the results that we present to the world. And in a lot of scenarios, what this means is that we're trying to find the global optimum, right? There are a lot of situations where if you've done a proper job of setting up your optimization problem, then finding a global minimizer means that you've recovered the ground truth. Or maybe the situation is a little bit fuzzier in modern machine learning, but finding a global optimizer maybe means that you found a classifier that fits data well and that potentially might generalize. But the point is that we actually have really strong expectations for our optimization methods. And so this distinction between easy and hard is important to us. Now, classically, the way we think about this distinction in optimization, at least the way that I was brought up to think about it, is between convex and non-convex problems, right? And convex are sort of these nice, well-structured, bowl-shaped objective functions. In many situations, if we found a convex formulation of a problem that we care about, we're done, right? We know that we can have efficient methods. Obviously, there's a tremendous amount of expertise and intellectual discipline that goes into developing and studying those methods. But from a formulation perspective, if we have a convex formulation, we're pretty happy. Conversely, the way that I sort of brought myself up to think is that if I'm over on the right side of this picture, then I'm in trouble, right? Then I really don't know much about what I'm doing. And so I'm going to work really hard to be on the left side. I'm going to try to formulate problems that are convex. And the challenge that we face is that applications tend to confront us with non-convex optimization problems. We'll talk about why a little bit later when we get into the talk, but for all of these exciting developments in engineering and technology, the optimization problems that we have to solve are non-convex. So although we have a really beautiful, well-structured theory for convex optimization, right? Which is almost a model for how to develop an area of computational mathematics. The applications are forcing us to go somewhere else. And that's a little bit tricky. If we take a worst case perspective, if we put on our theory hat and think about non-convex optimization in general, we know that non-convex optimization is impossible in general. And, it's formally hard, but we know that, really it's hard for very simple geometric reasons. And there are two geometric obstructions to non-convex optimization that I personally like to keep in mind that sort of reflect in the hardness results. One is, as we said, it's easy to make examples of non-convex functions with bad local minimizers, right? And these are function landscapes that are hard to navigate globally. The other one that when I was first entering this area, I found a little bit surprising is that it's actually possible to make objective functions with no local minimizers, but which are hard to optimize efficiently. And the reason is just that it's possible to make objective functions that are so flat that it's impossible to efficiently find a good direction to descend. So, usually we build our methods out of gradients capturing slope, Hessians capturing curvature, but you can make objective functions where those are not enough. And so you very rapidly get into hard problems in the numerical algebra of tensors. So these are two basic reasons why the worst case for non-convex optimization is kind of dismal. Okay, but that certainly shouldn't stop us from trying things. So with apologies to folks who have seen this before, I'd like to start the next portion of the talk with an experiment. The reason that I like to do this is just to point out the way in which some of the non-convex optimization problems that we encounter in practice differ from this worst case picture, to where maybe the typical behavior is not so bad. So the problem that I'd like to show you is not interesting in its own right, but it stands in for things that are very interesting. This is a model problem in image representation learning. So a la signal processing maybe about 10 years ago, what I'm going to do is I'm going to take a picture, I'm going to chunk it up into patches, and I'm going to try to learn a concise representation for those patches, right? So I'm going to try to find a concise encoding of the image. So in particular, what I'm going to do is take the patches, put them as columns of a big matrix, call that Y, and we're going to look for a factorization of that matrix. So I'm going to try to write Y is Q times X. And because I want a concise encoding, I'm going to try to make X sparse. Okay, so it's kind of a sparse dictionary learning problem, right? Given a data matrix, I'm going to factor that data matrix. Now, in this problem, because I'm learning from patches for a single image, I'm going to restrict my dictionary to be a square matrix. And in fact, I'm going to ask my dictionary to be orthogonal. So the columns of Q are orthonormal. So this is a restriction. We can, have a good conversation about when an orthogonal dictionary makes sense, when an overcomplete dictionary makes sense. Here, I'm sort of using this to illustrate a phenomenon in optimization, but it actually turns out that these orthogonal dictionaries are really not a bad idea in applications. So Psi, for example, has done some really beautiful work showing that you can do a lot of useful things in both in imaging and in medical image processing using orthogonal dictionaries. But here, I'm going to take an orthogonal dictionary simply because I'm learning for a single picture. Okay, so this is the setup. I have my matrix of patches. I'm going to try to factor that matrix. And I'm going to do it in a completely standard way, which is by solving a big optimization problem. So I'm going to minimize the misfit to the data, here measured in Frobenius norm, plus L1 norm, that's encouraging sparsity. And the only interesting aspect of it is here my Q is required to live on the orthogonal group, right? Because I'm trying to learn an orthogonal matrix. Okay, so this is a big optimization problem. Maybe before I go on, any questions about the setup here before I talk about properties of this optimization problem? Okay, so take that as no. So we have a big optimization problem, right? Two unknowns, the dictionary Q, right? These are the little building blocks that we're going to piece together to reconstruct our signal. I see there is a question in the chat. How do we even ask questions? I don't know, but I think you can either put them in the chat or you can unmute yourself and interrupt. I'm sort of fine with either, although maybe Sai will tell me there's a preferred method.
I think we would need to unmute them, John. So
you would need to unmute them. Okay, so
I
please,
think
if you have questions, put them in the chat.
I just unmuted Uluk Bek. So Bek, if you would like to speak, feel free to speak.
Hi, no, I just wanted to know, in the future I'll have questions, but for now I wanted just to test this. All right, thanks.
Wonderful.
Okay, you can also
there are two questions in the QA.
Right.
Is the L1 norm element-wise, and why the Frobenius norm specifically?
Good. I see. I didn't even see those questions. Interesting. Okay. Yes, the L1 norm is element-wise, right? We want X to be to have only a few non-zero entries. So this is applied element-wise. The Frobenius norm here is kind of a convenience, right? We know that there are probably better ways to measure correspondence between images. I mean, obviously Frobenius norm is well motivated if your model is structure plus Gaussian noise. But you know, here this is kind of a normal thing to do in dictionary learning and reasonable, but from an application perspective might not be the best possible. Okay, I see also a question, is the image gray level? In the examples that I'll show, it is, although you see similar phenomena if it's not. Okay, so great, so thanks. So this is our setup. So again, we're trying to find dictionary and coefficients by solving a big optimization problem, you know, constraint problem. Probably the first thing to note about this optimization problem is that it has a symmetry structure. What that means is that if I were to take the dictionary, right, collection of building blocks, and permute it, I get another dictionary with exactly the same representation power. So if I make the same permutation of my coefficients, I get exactly the same representation. It approximates Y just as well, it's just as sparse. So there's a sign permutation symmetry, right? What that means is that if I have one good solution, then I have a combinatorially large number of equally good solutions. And because of this, simply from this fact that the optimization problem is symmetric, I have that the optimization problem is non-convex, right? I have a minimizer here, I have a minimizer here, I have a minimizer here. The optimization problem, the optimization landscape sort of has to turn over in between. This is going to be a non-convex problem. Okay, so, you know, depending on our view on non-convex optimization, this might make us concerned about the prospect of finding good solutions, you know, or maybe not. One thing that we do know that we can do is we can develop methods. And so what I'd like to do here, at the risk of fumbling a little bit with the technology, is just show you what happens when you take a method and throw it at this problem. So the particular method that I'm going to show you is not that important in its own right, but is one that leverages the structure of this optimization problem to alternate between the X and the Q. So it turns out that it's an easy problem to solve for X with Q fixed. And it's also an easy problem to solve for Q with X fixed. So what we're going to do is we're going to start with a random guess at Q. right, completely unstructured, just choose it uniformly at random from the orthogonal group, and then bounce back and forth until we hopefully converge to something. Okay, so I'm going to switch my screen. So now you should be able to see Matlab, and I'm going to go ahead and run this method. So what's being plotted here is the objective function as a function of iteration. So iteration is on the x-axis, objective function was on the y-axis. We've just converged. This happens to be the thing that it converges to. These are the columns of the optimal dictionary visualized as little patches. This was the test image. I'm sorry, it's going by a little bit fast, but it's this grayscale image of the Golden Gate Bridge. What you can see in this graph as we start to run from another random initialization, that's the red curve, another random initialization, that's the yellow curve. Now, fourth random initialization, that's the purple curve, is that although the path that the method takes differs, it absolutely depends on initialization, it seems that the quality of the solution that it finds actually doesn't, right? In these experiments, I'm always converging to something with the same objective value. I may not know, it may not always be exactly the same thing, right? There's a permutation ambiguity that we talked about earlier, but at least I'm always finding something of the same quality, no matter where I start. And so that's interesting. It doesn't yet say that we're finding global solutions, right? Maybe there's something better off in some obscure corner of the space, right? We need mathematics to say that we're finding global solutions. But at least there's some interesting structure here that seems to differ a little bit from the worst case picture that we talked about earlier. Okay, Kotaro Asai asks in the chat, does this look like the design of vector quantizer by iteration? So I think that there are a couple of ways to answer that. One is in terms, so first of all, I'll say that I'm not a, there are probably folks on the chat, folks in the chat with more expertise than me in design of vector quantizers. So I apologize if I say something naive, but I think structurally the optimization method is similar in spirit to methods for designing vector quantizers, right? Like in particular, you can see the dictionary step and the coefficient step as finding a representation and then finding a dictionary, right? Like finding a representation and then representing the data with respect to it. So this is similar in spirit to things like k-means or expectation maximization for clustering. The thing that I'm trying to point out in this experiment, which is interesting, is that at least for this problem, that iteration, which sort of by rights has kind of no right to do anything all that useful, right? It's a non-convex problem. It's a kind of naive method. In this situation is actually always finding good solutions. So that's what I'm sort of trying to highlight here. It turns out that there's some geometric explanations for this. We'll get into them as we go into the talk. And those geometric explanations actually do have some relationship to vector quantizer design and clustering. Although those problems, we can talk technically why, those problems can be harder sometimes. But yeah, I would say that both conceptually and in some of the phenomena, there's a pretty close relationship. Okay, and thank you for the question. Okay.
John, I have a question for you.
Yeah, please, Sai.
Wouldn't you say that this sort of behavior is also a function of the specific algorithm as well?
I think, let me just close this before my computer explodes. Yeah, is the behavior a function of the specific algorithm? So I'm going to say no. That's not precisely true in the sense that you can, I think that you can find algorithms that will not provide this behavior, but most reasonable algorithms when applied to this problem will. In particular, right now we're alternating between dictionary and coefficients, but if instead, for example, you smoothed out the landscape a little bit and then did gradient descent, you would see something similar. If you smoothed out the landscape a little bit and then did a higher order method, like a trust region method, you would see something similar. So what I'm going to try to highlight through the talk are some of the geometric reasons for these kinds of phenomena. And those geometric reasons seem to be somewhat method independent. So it's sort of like what's important here is the formulation. Being on an orthogonal group seems to help. The sparsification seems to help. The data. And once you have those, then any reasonable method seems to produce about the same behavior. Does that answer your question?
Yeah, yeah.
Okay.
And could you also maybe shed some insight, some light on just, you're talking about the orthogonal group, and
yeah, good.
If it's really a general overcomplete dictionary, then sort of empirical evidence suggests that you may not get this pleasant of a behavior with a general overcomplete dictionary, right? So maybe you'll talk about it in your talk as well, or
I won't show you any strong results for overcomplete dictionaries. But yeah, it's a very good question because often in practice, people prefer to learn overcomplete representations. And for overcomplete representations, we have to be a little bit, as you say, we have to be a little bit careful. In particular, even if the dictionary is known, it's not always the case that I can recover the sparse coefficients, right? That this is only under certain hypotheses, both on the dictionaries and on the data. So, already when we talk about the overcomplete case, there's that issue. Then when we also throw learning the dictionary in, the picture becomes messier. So there are theoretical results in this vein on learning overcomplete dictionaries. There are various sort of tricks that you can play to start out in a good portion of the space where you don't tend to run into bad minimizers. Also, if everything is nice enough, then a lot of that smooths out and you can find good dictionaries from random initialization. But I agree that the whole thing gets more complicated. This orthogonal dictionary learning is interesting. Like it's really a rock, right? You throw it real data and as many initializations as you want, and it just always gets you the right answer. But yeah, it's a good question.
Thanks.
Sure. All right. So thank you everyone for the questions, and please keep them coming as we go. Maybe what I'll do for now is to, in the interest of time, to move forward a little bit. So, this is representative of this sort of theory practice gap, right? Like often in practice, non-convex methods do very interesting and very useful things. And the worst case theory really doesn't reflect this. So how can we understand this? So trying to understand this has been an undertaking for the field as a whole, over the past 5 or 10 years. There have been a lot of interesting developments, mostly looking at very simple non-convex problems. The ones that we'll talk about today are very simple. These are the ones that we can understand. Some of the most interesting ones are still wide open. There are beautiful phenomena that we really don't know how to explain mathematically, at least in a rigorous fashion. But there has been some development. The way that I personally like to think about this development is in terms of the symmetry structure of the problems that we're trying to solve, right? In dictionary learning, we're non-convex because we have a permutation symmetry. And it turns out that that symmetry structure is also the key to understanding why methods can succeed. So at a slogan level, for certain symmetric problems, you have nice geometry that gets you good solutions. So what I'd like to do for the rest of the talk is just very briefly show you how that plays out in a couple of simple model problems. You know, Sai asked the right question earlier, which is what about more complicated problems? Here we're going to think about some simple ones. These are the ones that we can understand. And we'll tell you about a few theoretical results. We'll also try to extract some intuitions that we hope carry over to more challenging situations. Okay, so if we're talking about non-convex optimization, there is one simple non-convex optimization problem that many of us solve every day. This is the eigenvector-eigenvalue problem of optimizing a quadratic form over the sphere. So in this problem, my objective function is x transpose ax, where A is a symmetric matrix, and x, kind of like our Q before, is constrained. Here, x is constrained to have unit L2 norm. The reason that this problem is interesting computationally is that the critical points of this problem are the eigenvectors of the matrix A, right? If I look at the condition for the objective function to be stationary over the sphere, the derivative of x transpose ax, that's twice ax, needs to be proportional to x. And so every critical point is an eigenvector. I'll say I like to lead with this one because this is the one example that we can do on a piece of paper without, you know, needing a lot of complicated computations or, you know, a lot of elbow grease. So if there are students on the call, like this is the one that you can go back and think about afterwards. And if you think about it, first thing that you show is that every critical point is an eigenvector of A. Second thing is if you look at the right notion of curvature over the sphere, right? If you want to know what kind of critical points they are, so you look at the second derivative intrinsically on the sphere, what you'll find is that the minimizers are tail eigenvectors corresponding to smallest eigenvalue. Maximizers are lead eigenvectors corresponding to largest eigenvalue. And everything in between is a saddle point, which you can show has a direction of strict negative curvature. So what that means is that this is actually an optimization problem that we can solve, even it's non-convex. In particular, this is a problem that has no spurious local minimizers, right? Every local minimizer is global, and every other critical point has a direction of strict negative curvature. So both of these worst case obstructions disappear in this situation. There's none of this exponentially many bad minimizers, and there's none of this too flat to find a direction of descent. Okay, as we said, so this is one that we can solve. Now, when we think about the behavior of methods on this landscape, it's useful to think about them in terms of the local geometry. We capture that local geometry, as we said, in terms of slopes and curvatures, right? What we would like technically is that at every point that's not close to a global minimizer, I either have a strong gradient or I have a direction of strict negative curvature. And so in this talk, I'm trying to keep things at the level of pictures and intuitions for the most part. But when you get down to analyze methods, if you put some parameters on all of this, then you can say something about how quickly your favorite optimization method gets to a minimizer. Okay, so this is kind of the local picture. And for the eigenvector problem, this local picture is enough. For dictionary learning, we need to think about a little bit more of a global picture, right? Because we have all of these equivalent solutions, we need to know how this plays out. So what I'm going to do is to show you how this plays out in kind of a baby version of the dictionary learning problem. Sai already alluded to the fact that we're not solving the most general version. Here, we're going to constrain things even a little bit more to make some theoretical progress and get some rigorous intuition. So, bear with there. Of course, it's a valid question, what are the broad, what, if anything, are the broad implications of this? But, we're going to restrict it and try to understand. So in the problem that I'm going to study, as a theoretical convenience, I'm going to imagine that there's a true dictionary out there in the world that I'm trying to find. So I'm going to imagine that the data are generated as dictionary times coefficients. So there's a Q0 and X0, and my problem is to find them. And I'm going to make two restrictions. The first one we already talked about. The major restriction is that I'm going to ask Q to be square and invertible. The kind of technical convenience that makes it possible to do analysis is I'm going to ask X to be a sparse random matrix. And so the kind of parameters of the problem are how sparse is that random matrix, right? If X is sparser, I'm looking for a simpler representation, the problem is easier. Then maybe the other parameter is the amount of data that I've seen. As I see more data, the problem gets easier. Okay, but this is my setup for trying to do theory. Q is square and invertible, and I imagine that there's a true Q that I'm trying to find. The reason that square and invertible makes life so much easier is now Q doesn't have a null space, right? Q is a full rank matrix. And so in particular, that gives me a degree of freedom to either think about the problem of learning a dictionary in terms of the columns of the representation or in terms of the rows. The reason that I can think in terms of the rows in this setting is that because Q is square and invertible, the row space of Y is the same as the row space of X. So if I want, I can either think about my dictionary learning problem as finding sparse columns that reproduce Y, or I can kind of think about it as finding sparse rows in the row space of X. So I have this kind of funny, it's this kind of funny geometric problem of you have the row space of the data matrix, that's this gray subspace here. It contains some sparse vectors, those are the rows of X0. Let's see if we can find them. Okay, and just to butcher the problem just a little bit more to make our life just a little bit easier, we're going to try to find those vectors one at a time. So what this is going to correspond to is finding the atoms of the dictionary one at a time. In practice, finding them all at once is better, but it's harder to analyze. So here we're going to analyze a simpler version, and then hopefully that gives us some intuition for the things that we would really like to do. So I'm going to find them one at a time simply by looking for directions that make the coefficients sparse. So I'm going to try to minimize the L1 norm encouraging sparsity of Q transpose Y. Here, Q is going to correspond to a column of the true dictionary, Q0. So that's what we're trying to find. So if Q0 was orthogonal, then Q should be a unit vector. So instead of minimizing loss plus regularizer over the orthogonal group, now I'm minimizing regularizer over the sphere. Okay, so minimize L1 norm of Q transpose Y such that norm of Q22 is equal to 1. And when I do analysis, I'm going to use the fact that as I accrue more data in this model, it becomes more and more regular, right? Formally, the objective function here is the sum of independent random variables. But this is the problem that I'm actually going to analyze mathematically. Find a sparse combination of the rows of Y, make the coefficients of that combination unit L2 norm. Okay, and the nice thing about boiling this problem down to a model problem is now I can visualize it. So this is an example in 3 dimensions. This is actually the objective function of this learning problem, visualized as a function over the sphere. Blue is small objective, yellow is big objective. The red points here correspond to the columns of the true dictionary. So those are our target solutions. you can see there's kind of a symmetry structure to it in the sense that what was our permutation symmetry before now corresponds to not knowing which atom we're going to find. So instead of exponentially many equivalent solutions, now I have about 2n equivalent solutions in this picture. Those are the red points. And the thing to notice about this landscape is that although it's very much non-convex, we're on a sphere and the objective function has this symmetry to it, there's a lot going on here. It's also pretty nice. In particular, if you squint at it, you can kind of convince yourself that in this simulation, the only minimizers are these columns of the truth. There are some maximizers at the yellow points. There are a lot of saddle points, actually exponentially many saddle points in high dimensions, but the only minimizers are the truth. This is just another way of visualizing the same object. This is visualizing the objective value as a height, like above the equatorial plane. And so what you can see, intuitively speaking, is that instead of having a convex function, like we might have looked for classically, here we have a non-convex function that almost acts like a symmetrization of a concave. It's like you took a basic concave pattern and then you stamped it down here, 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 here. And it's not too difficult to convince yourself that even you start near the top of the hill, you're going to roll down to one of these good solutions. You won't know which one ahead of time, but you know you'll find one of them. You know you won't get stuck. So this is the geometric intuition. Now, in truth, we don't do this with a lot of data, right? We only do it with a finite amount of data. So at a technical level, we have to control that. So we have to show that the objective landscape becomes nice when we have enough data. But what you can obtain if you do that analysis is you can obtain a theorem that says that in this model, if you've seen enough data, then this is an optimization problem that you can solve globally efficiently from arbitrary initializations. So, you know, that's more or less what the mathematics says. I mean, here it's kind of sketched, but it basically says that this is the picture in general. Now, if you're really a connoisseur of theory of dictionary learning, there are some senses in which this improves over some previous, theoretical results in that area. In particular, an interesting thing here is that the representation doesn't have to be super sparse for this to work. And that's actually interesting from this convex, non-convex perspective. You can there are ways to kind of torture this dictionary learning problem when it's really, really sparse. You sort of turn it into a sequence of linear programs and then you can get a result. But those things break down as the problem becomes denser. And so, what this says is if you just solve a natural non-convex problem, actually, even for fairly dense matrices X, that still works. And it works in this kind of strong sense. Let me see. There's a question in the Q&A. Okay, I'm sorry, I've lost the Q&A. What properties should, Hassan asks, what properties should H mu have? Okay, yeah, so thanks Hassan. So that's good. So that was a detail that I skipped. So in the analysis, you need to use both slope and curvature, right? Curvature is really important here. In some sense, negative curvature is the key because that's what tells you that you don't get stuck. And so when we do analysis, we smooth out the L1 norm, and we analyze that. And so this H mu in the theorem is a particular smooth sparsity surrogate, but the phenomena is the same for other smooth sparsity surrogates. It seems to not matter that much. It's just sort of after you've written 100 pages about one of them, you don't want to do it again. But yeah, it would be better to have general results that sort of hold for anything that's close to an L1 norm. And empirically, that seems to be the case. So, I think there's more that could be done there. Sai says Hassan, I enabled. Hassan, does that answer your question?
Yes, thanks, John.
Okay, wonderful. Good. So that's the upshot. This is it sort of theoretically, this is it pictorially. Now, it happens if you care about algorithmic theory, you can recover the whole dictionary by doing this one at a time thing. It's not, it's not a terrible method. But I think what's really most interesting here conceptually is the picture that, like, underlying this non-convex optimization problem is this kind of nice geometry that is really just a function of the symmetry structure of the problem. So for this particular problem, you're non-convex because of symmetry. And in some sense, that's all that's going on. So if you can wrestle with that a little bit mathematically, you find that indeed everything seems to be okay. Okay, so what I'd like to do next is I'd like to take just a little bit of a detour and show you how a similar structure plays out in a problem that's probably a little bit closer to computational imaging practice, and that's in a variant of the sparse blind deconvolution problem. I like to motivate this from an application perspective. So we sort of so sparse blind deconvolution is an important general problem. People do it in astronomy, people do it in neuroscience, people do it in general image deblurring with a gradient sparsity. So this is used all over the place. I was sort of dragged into this through an application in electron microscopy. This is joint work with a bypassopathy. He does condensed matter physics. If I had more than 10 minutes, I would tell you more about all of the amazing stuff that they do. But we're just going to use this as an example to drive the discussion. So they're interested in solid state materials. In particular, they're interested in high temperature superconductivity. To study these materials, they take measurements where they raster this atomically sharp tip around. They record either a current or a voltage between the tip and the surface, and this gives you an image. And it turns out, if you're really, really careful about this and you do it in kind of an open loop fashion, then you can actually record two independent measurements. And so what you get out of this, finally, what I'll sort of hand to us as signal and image processors is a cube. So your observation here is a cube. It has dimensions of space, x, y, and energy, say the applied voltage between the tip and the sample. And what this measurement is telling you is something about the quantum mechanical properties of the material, like telling you about occupancy at different points in space and at different energy levels. And what people are interested in learning from this measurement is something about the state of matter of the material, something about its structure, as this sort of influences its electronic properties. Now, fortunately for us, this boils down to a pretty simple problem in signal processing, which is one of finding repeated motifs in data. So it turns out that the interesting thing in this cube are sort of local perturbations due to the presence of dopants. This is what gives the material its interesting and useful properties. And so, here, these are visualized as these kind of ripples around a little depression. Here is the same thing in a relatively sparse sample. So you have these little repeated motifs. Like at left, they look like little O's. At right, they have this kind of elongated structure. And what's shown here are two different energy levels. So these motifs occur at particular places in space across energy levels. And the basic data analysis task here, which is shared with model versions of neural spike sorting and some problems in astronomy, is to figure out what are these basic motifs and where are they showing up in my signal. Okay, so I want to find these things given the data set. And I'll say, because I don't know much about the property of the material ahead of time, I don't ahead of time know what the motif signature is, nor do I know where it's occurring. So you can already see this is a kind of blind deconvolution problem, right? If you show this problem to a signal processor, they're immediately going to think of a convolutional model. They're going to say, well, you have your data set. That can be represented as the effect of stamping my motif here, 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 here. Let me write that model as a convolution between the motif signature and a spike train that tells me where that thing shows up. So I have more or less y is a convolved with x, maybe plus noise. So very similar problem to what we saw in the first half of the talk, except that now this one is convolutional. And my goal, given y, is to find a and x. Okay, and so, again, computationally, all of us pretty much know what to do. We're going to write down an optimization model that contains fidelity to observed data, sparsity, and maybe some kind of a constraint on A to break the scale ambiguity. Now, I'll say, if you're interested in deconvolution, especially from the theory perspective, there are a lot of different models out there. Here, we like to refer to this one as a short and sparse model. It's short in the sense that the A has relatively small spatial signature, and the X, we hope, is relatively sparse, right? So those are the structural assumptions that we're using to make this ill-posed inverse problem well-posed. Once we have those structural assumptions, then we solve it by optimization. Again, we have data fidelity, we have sparsity. Probably the only thing that's interesting in this formulation is that here I'm constraining my A, again, to live on a compact manifold, which this time is going to be a sphere. I constrain it to have unit L2 norm. And that's actually kind of important when you dig into the geometry, because this curvature that we saw earlier actually comes from an interaction between the curvature of the objective function and the curvature of the constraint set. And so both are important in sort of giving you a landscape that smooths out and hopefully doesn't have too many bad local minimizers, or in some situations maybe even has none. So natural objective function, sphere constraint. Now, instead of a permutation symmetry, this problem is a convolution problem. We have a shift symmetry. The way that plays out is if I have a good solution, if I have an A and an X, if I shift A to the left by, say, S units, and I shift X to the right by S units, their convolution stays the same. And X stays sparse. So instead of combinatorially many equally good solutions corresponding to permutations, here I have a smaller number of equally good solutions corresponding to shifts of the ground truth. Okay, and what the simulations show is kind of like what we saw earlier. If the data indeed follow this model and you set things up appropriately, then you tend to find one of those equivalent solutions. So this is showing that with some simulated microscopy data. This is showing that with some real microscopy data. It has advantages over what people in this particular area were commonly doing before, which was more based on sort of hand inspection of the Fourier transform, right? You sort of get these nice clean defect signatures. For our purpose here, I think what's interesting for us to contemplate is, what does this tell us about geometry of optimization? Okay, and so we can kind of do the same thing that we did for dictionary learning. We're going to make a baby model for the problem, And then we're going to probe its geometry. And we'll sort of get two artifacts out of that. One is we'll get some theoretical results that say that there are situations where I can provably solve this problem with an efficient method. And the other thing, which I think is at least as interesting, is we'll get some pictures and some intuitions for sort of how and why this is working. So here I'm going to go pretty quickly, and I'm going to focus mostly on the pictures and intuitions. We're almost at time, so I won't say too much in depth about the theory. The theory pertains to this short and sparse model. Here we're doing it in one dimension instead of more. As in dictionary learning, we need some technical assumptions to make it work. In particular, here what I'm asking is, again, that the X is a sparse random signal. That's kind of the technical convenience. And then the major restriction is I'm asking these target solutions A0 to be shift incoherent. That means that if I shift one of them, the resulting thing is not too nearby. And it's sort of intuitive. That's probably not the best thing, but it's sort of intuitive that you would need something like that, simply because from basic signal processing, we know that as the kernel becomes smooth or low pass, then the problem becomes harder to solve, and we're going to need X to be sparser. So, somehow these two requirements should be in tension. And the theory articulates a tension between them. In particular, if the kernel is really spiky, then the X can be dense. If the kernel is not very spiky, then the X needs to be really sparse. And let's see, Q&A. I thought there was something in the Q&A. Okay. So there's a trade-off between sort of density of the X and niceness of the kernel, which is expected. As before, this is an area that is still developing. We're still learning how to do this kind of mathematics. And so to get results, we need to sort of play with the problem a little bit. Here, we're going to play with it by making an approximation to the objective function. So the approximate objective function is not as good as the one that we started out with, but it's one that we can analyze. When we settle in to analyze that approximate objective function, what we find is actually a very similar thing to what we saw before. So this is what the objective function looks like in the vicinity of a shift of the ground truth. So you can see there's this kind of nice bowl-shaped geometry. So you're strongly convex around a minimizer. If I take the span of two shifts of the ground truth, then I see two minimizers, and in between I have negative curvature, right? So again, I don't know which minimizer I'm going to find. I don't know which shift I'm going to find, but if this is really the picture in general, I'm going to find one of them, right? Negative curvature takes me to one or the other. And what I get in higher dimensions when I consider more shifts is this kind of egg carton-like structure where each minimizer has a region of strong convexity around it. In between, there's negative curvature in directions that break symmetry. And because of this, I can expect to find minimizers with reasonable optimization methods. Okay, and so the theory proves that this nice geometry obtains over a certain subset of the sphere where we're in the span of a few shifts of the truth. And then that turns out to be enough to have a provable method. So you sort of have nice geometry where you need it. So this is the geometric theorem. I'm going way too fast to ingest this at anything beyond a sort of impressionistic level, but the aspects of the theorem that are interesting, one is that this is behavior that obtains when you have enough data. That's as before. Two is that this is behavior that obtains when you have the right trade-offs between sparsity and coherence, right? So there's this tension between the target X being sparse enough and the kernel being nice enough. And that based on this theory, you can get a method that finds a minimizer. In particular, you initialize with a chunk of data, then you use your favorite optimization method, and you indeed find a copy of the truth. Okay, so I'm sorry to be a little bit rushed through this section. What I really hope that I was able to make clear is not so much the technicalities and the technical assumption, but really this picture. So in deconvolution problems, we have roughly the same structure that we saw in dictionary learning. Instead of a permutation symmetry, we have a shift symmetry. And the shift symmetry gives us this nice egg carton-like structure where, you know, again, I'm going to tend not to get stuck. I have local minimizers global, and I have good negative curvature. Okay, so Sai, sorry, Sai, you just, there's somebody just muted. Yes? Question?
Yeah, there were two questions in the
Ah,
Q&A.
okay,
So
wonderful.
I had,
I'm sprinting to try to finish, but I'm very happy to stop to take questions.
We can hold off until you finish, John.
Okay, yeah, I'm kind of fine either way. I mean, would folks like to ask the question right now? We can go ahead.
Okay, so there were two questions by Ganeshan and Arindam. And
okay, I'm sorry, somehow they're not showing up in my chat.
That's in the Q&A. So
oh, the Q&A is not the chat. Okay,
Ganeshan,
I don't know how to see the Q&A.
Arindam. Okay, so if we can just, I can just.
Yeah, why don't we just finish, and then that way folks who have somewhere else to be will be able to leave and such. Okay.
Okay, so the first question is from. Oh, you're saying.
Oh yeah, no, go ahead. I'm sorry. Now we're fumbling. Yeah, go ahead and ask the question. Whoever has the question.
Okay, so the first question is, does the symmetry work when Y has observation noise? And I think this may be for the.
Okay, good. Yeah, so what happens in noise? So our theory, so our published theory for dictionary learning and for deconvolution has no noise in it. It would not be a hard technical problem to do a noisy version of each of these results. So I think you could, yeah, and for baby versions of dictionary learning, like if you make the problem really sparse, it's really not too hard to get that to come through. So, you know, I think what you would expect if you add noise is that you still have a nice landscape. Now, the minimizers in noise won't be at exactly the truth, right? Like there's a sort of perturbation that's going to be roughly corresponding to the noise level. But all of these other phenomena that you need, like the gradient and the Hessian, are sort of stable with respect to noise, and so I think it's possible to prove something in that setting. So theoretically, you add IID noise, you should be fine. Now, I think the interesting question from an application perspective, like when we go to the electron microscopy, is you have all kinds of other structure noise, you know, like in that application, scan lines are wrong. There's all kinds of stuff that's not IID noise that can go wrong. And so it's interesting to see like how robust all of this would be to those kind of perturbations. But for IID Gaussian noise, I think everything should be fine and should still work.
Okay, maybe we'll just take one other question and then you can spring forward, right? So
sure.
The second
Sounds
question,
good.
Does higher order statistics help in better optimization instead of this square form or sphere?
Okay, yeah, so that's a good question. I think that there are a couple of things to be said there. So one is that I don't know how to say anything rigorous about that question. I do think that there are like two aspects to it. One aspect is modeling, and then the other aspect is optimization. From a modeling perspective, obviously, if you incorporate more information about yeah, if you incorporate more information about either the structure or the noise, you can sort of, on general principles, you sort of expect that you would be able to do better. The question is like, will that break the nice properties of the optimization? And so some of my colleagues do have a little bit of work, in particular, Yutian Zhang, who did a lot of the theory here, has some investigation into what, for example, what happens if you turn that P norm or that 2 norm into a different P norm? What happens if you change the objective function? And we don't have strong results, but there are some preliminary indications, number one, that it can be fine. And number two, that there's an interesting matching between objective and constraint, like, because you kind of have a freedom in choosing the constraint as well. And so making them compatible in some sense seems to be helpful for finding good solutions. In some sense, in the results that I've talked about, this negative curvature is always an interplay between the objective and the constraint. And this L1 type objectives seem to play very nicely with a sphere constraint. As you change the objective, then you may also need to change the constraint to get good geometry. These are all like very rough intuitions. A lot of these things I haven't tried in too much depth, but these are my feelings. And thanks for the question. It's a good one. I wish I had better things to say about it.
Hello. Yeah, thank you very much.
Okay,
yeah,
great.
I have actually, I was asking the question. So thank you very
okay,
much
wonderful.
for that.
Yeah, thank you for the question.
Yeah.
All right. So I'll skip the comparison with the literature. I'll say that the constraint actually matters. So it turns out you can do pretty reasonable image deblurring just by choosing the right constraint and getting the optimization right. This is a comparison to other formulations in computer vision. Also, if you understand the geometry, then in some situations it becomes possible to incorporate additional prior knowledge. This is calcium imaging using some knowledge about the spike patterns. These are just more examples of this kind of thing working out. What I'd like to do to close is just bring things back to some extent to the broader picture. So we've seen two examples, dictionary learning and sparse blind deconvolution. In both of these problems, we have this symmetry structure that forces us to deal with non-convexity, but the non-convexity that we have to deal with turns out to be kind of mild. If we can dig in and understand how symmetry affects geometry, then in some versions of these problems, we actually have no spurious optimizers. And we can build methods that find the ground truth. Underlying all of this is this kind of nice geometric picture where symmetry shapes the landscape of optimization. And in thinking about this area in general, I like to think about it in terms of the symmetry groups. So it turns out that there's a rough classification of problems. If you like matrix completion, matrix sensing, generalized phase retrieval, if you're familiar with these are problems that typically have continuous symmetries and they exhibit similar landscapes. You can see here this continuous degree of freedom. These are problems that are often amenable to SDP relaxation. They're amenable to convexification, but non-convex methods are more efficient. And this sort of symmetry perspective can help you to dig into why they work well. The class of problems that I think is especially intriguing and that we still don't understand very well are problems with discrete symmetries. And these include things like deconvolution in dictionary learning, which we saw earlier, also certain forms of tensor decomposition. There's nice work by Runga and collaborators. But a lot of the problems that we don't understand also fall into this class. And so, if you're a theorist trying to come up with better tools and better approaches to handling problems with discrete symmetry is, I think, a very interesting direction. In particular, neural networks, we know very little. They have a lot of discrete symmetries corresponding to reordering of the neurons, maybe Fourier phase retrieval. there are a lot of interesting things that we don't understand very well in this class. Also, these problems with discrete symmetry are typically the ones that we don't know how to convexify, right? We don't know how to convexify dictionary learning. We don't know how to convexify this particular deconvolution problem. So we kind of have to be non-convex. So understanding this geometry becomes important. And then finally, there are some beautiful phenomena and interesting open questions around the behavior of the simplest method of them all, which is randomly initialized gradient descent. So, you know, more or less any natural method works, but when you try to really quantify that, understanding how gradient descent interacts with this symmetric landscape is interesting, and there's still a lot to do. Okay, so with that, I think I will close on this picture, or maybe on a thank you to my collaborators. So thank you to all of them. Thank you to Sai and the organizers. Thank you to all of you for your questions and simply for being here. You know, I had fun. I appreciate it. Thank you. And I'll be happy to take any further questions.
Thank you, John. That was a really interesting talk. I think we have like a few questions in the Q&A.
Okay, great.
And the first question is by Saeed Saneh, and I'm going to try to make this interactive.
Okay, excellent. So Saeed asks, you're unmuting Saeed. So Saeed asks, what can be the role of initialization here?
Right, I think he's left actually. I can't find.
Okay, well, I can answer it for everybody else. So I showed, okay, so there are several things. So in the theoretical literature, you'll see results with initialization. You'll see results without initialization. Our dictionary learning results don't require any special initialization. The objective function is globally nice. Our deconvolution results only characterize the objective function on a subset of the space, and so they do require initialization for the theory. Practically speaking, random initialization is totally fine. And it's interesting to try to explain that theoretically. I think for dictionary learning, we have a pretty good theoretical explanation. For deconvolution, it's more technical difficulties rather than conceptual difficulties. The technical difficulty is, you know, for those of you who work in sparse approximation, usually when we analyze sparse approximation methods, we assume that there's a true solution that we're trying to recover, and that's the basis of our analysis. And that works when you have the right dictionary or when you have the right filter for deconvolution. But analyzing things in like the hinterlands where your filter is very bad or your dictionary is very bad is where the challenges show up. And so, you know, for a deconvolution, I think eventually probably someone will get a global result, but you know, right now we don't quite have the muscles. But you know, I think the phenomena is that often random initialization works. Then in the theory, in the theoretical literature, there's also discussion about initialization as a way to improve computational performance. That I think is interesting as well, because you know, if there's a way to start closer to the truth, absolutely nothing wrong with that. For deconvolution, there actually is a good way of doing this. You can kind of initialize with the data itself, which are superpositions of shifts. So yeah, I think that's more or less the role of initialization here. And if Saeed was here, I would ask if we answered the question, but I guess we're good. Let's see. So Beal asks, in all symmetry structured problems, you have mentioned it would be easy to remove the symmetry ambiguity. This is a really good question. And this is one that haunted me for a couple of years, because when you see these problems, you want to be clever, right? Like you want to say, I can get rid of symmetry. For example, in the deconvolution problem, I'm going to constrain the center of mass to be at the origin or something like this. Or in the dictionary learning problem, I mean, when I first started working in this area, I tried all kinds of crazy stuff. Like you can put a sorting constraint on the dictionary elements that gets rid of the permutation ambiguity. The challenge that you have is when you start trying to be clever, in some sense, you start doing things that go against nature in the following sense. So usually what you do is you make some constraints and you optimize the loss over those constraints. For example, if you put an ordering constraint on the dictionary atoms, you know, say the first element of each atom needs to be in decreasing order, then you end up with an additional constraint which is kind of elongated and not very well shaped. And when you go to optimize the loss over that constraint set, the loss doesn't know you're optimizing over that constraint set. It just says, I'm the loss. I want you to go to one of these solutions. So typically it will try to take you to an equivalent solution that is not the one that is in that symmetry cell. And so it'll actually pull you towards the boundary of that set. And you'll actually introduce spurious local minimizers by adding those constraints. And a few years ago, I felt very frustrated by this phenomenon because I felt like it should be easy to get rid of symmetry and, you know, just think about one solution. But I've sort of started to see it as a nice thing that, you know, the loss wants to take you to one of them. And so, you know, you can just let it do that for you. It could also be that there are other clever ways of getting rid of symmetry that I haven't mentioned that work. I mean, one question that often comes up is there some way to optimize over a quotient space? So like you take a quotient by the symmetry group. And that feels really natural mathematically, and you sort of feel good after you have that idea because it feels very clean. But then you have to think about how to do that. You find that you're still not convex over the quotient. You don't actually know how to make that partition ahead of time unless you know the ground truth. And so, you know, somehow it gets very messy very fast. So I guess maybe the simplest and most transparent answer to Beal's question is, when it comes to getting rid of symmetry in the formulation, I've tried really hard and I don't know how to do it. And I'm happy to just leave it in there, but maybe somebody else will come up with some good way of doing it.
Great, thanks a lot.
Okay.
Let symmetry do the work for you. That's awesome.
Great, thank you.
Thanks.
Okay, so the next question is, in the convergence results you showed for dictionary learning, what happens if we run the algorithm with the simulated Y? That is by inserting our own Q and sparse X. Ah, I see. So if you redid the first experiment with the simulated data, then yeah, it always converges to the true solution up to this sign permutation. So yeah, I showed the real data experiment first because somehow two reasons. Actually, that was what first got me into this area. Actually, we had been trying really hard to find good convexifications for dictionary learning, and this non-convex method was kind of a last resort. It was like, after all the fancy stuff didn't work, let's just try the simple thing. And when that also doesn't work, then we can know that we can't solve the problem, we'll give up. And then, you know, you throw it at images and it works. And that's surprising because usually you sort of expect that real data are messy in some way, that they have some structure that doesn't show up in the planted model. But at least for the orthobasis learning, it seems like there's something really solid there. Okay. Did I answer the question?
Yes, thanks.
Okay, wonderful. Next is from Ryan. Ryan asks, have evolutionary algorithms been explored for non-gradient based optimization of non-convex problems like those discussed? So I think genetic algorithms are like one of those suggestions that is always is always like is available to you for any problem. And so I'm sure that if we were to go to Google Scholar, we would find papers that are using genetic algorithms to solve these kinds of problems. And I would suspect that they're probably getting reasonable results by doing it. I think where genetic algorithms really shine, in my own like really limited experience, probably you have more expertise on this than I do, but I think where they really shine is in giving you a way to navigate things like this kind of nasty landscape that I showed at the beginning, where you have all of these, you have all of these local minimizers and you need some sort of global search mechanism, especially if this notion of sort of breeding and recombination and random mutation plays well with the structure of the problem. I think for these problems, just like you wouldn't, so for example, you wouldn't use a genetic algorithm to solve a linear programming problem, because linear programming is like well enough structured that people have been able to think about it for a long time and really understand the structure of the problem and come up with good specific methods. I think a question is, are the problems that I described here more like linear programming, or are they more like that horrible worst case that I showed in the beginning where you need global search? And I would personally sort of contend that they're more like linear programming, like we're trying to understand structures of the problem and we have glimpses of a few things that come through. But maybe that's open. I think this is a young area. And of course, it never hurts to try things, so
yeah,
that's my feeling.
Okay, yeah, thank you. I'm certainly no expert, but I'm actually taking a class and learning about optimization and evolutionary algorithms. So I was just curious about how that it might apply to what some of the stuff that you did. So yeah, thank you. That really answered.
Yeah, great. Yeah, it's a good question. Thank you. Okay. So Robert asks, could I contact you for convex optimization problem? So you're welcome to send me a note. There are people who have more expertise on methods for convex optimization. And also, if you're just trying to get a good solver, there are increasingly good sort of open source methodologies for doing this. Like if you have a small problem, the CVX package is absolutely gorgeous. And there are other things that that you can try as well. But yeah, you're welcome to send me a note. Maybe I can point you in the direction of some of those things.
So there is one more question in the chat.
Okay.
By Sadeed, and I've enabled him to speak.
Saeed. So Saeed asks a really nice question. So typically when we do signal processing, at least if we're from the optimization camp and we sort of indoctrinated ourselves in compressed sensing and things like that, when we do signal processing, the first thing that we try to do is to find a convex relaxation. And for these problems, you don't have a convex relaxation. So the next thing that Saeed suggests is, can we have a non-convex relaxation? Is there a way of approximating a general problem with something that has some kind of nice structure to it? And I think that the short answer is I don't know. The long answer is I don't know. But I think that I'm really interested in this question. I think for the kind of stuff that we're talking about here to work, you need to start out with a symmetry structure, or at least a near symmetry structure. Then the question is, given that you have a symmetry structure in your problem, how can you build a formulation that plays nice with it? Because what we've done so far is we've analyzed a few formulations that turn out to play nice, but what is a well-structured methodology? And I've been trying to work on this question for a couple of years. It's also related to the theory, because I think, if you start trying to read these papers, papers in this area tend to be pretty hard to read. And I think that reflects that we don't have great tools. We have to do a lot of things by hand on a case-by-case basis. And so we need better tools. There are a couple of attractive directions for that. There are a couple that I really like. One is by sort of trying to look at sum of squares certificates for the absence of spurious minimizers. Another is, in nature, there are certain variational formulations that automatically have no spurious minimizers, right? Like if you think about, like a circus tent, right? There are some poles that are the solutions and then everything else smooths out so that every maximizer is global. So there are a couple of like fun conceptual avenues to trying to do something like that, but actually making it work at a technical level seems quite challenging. At least personally, I haven't got great results there, but I love it as a question. I think it's a great direction.
I think that's about it. There was
I
a
have a-
follow-up from Robert asking your email, but I think maybe you could text him or something.
Sure.
I have a question to John.
Sure.
Yeah. So you said that generalized phase retrieval problem is a nice non-convex problem, but you also mentioned that Fourier phase retrieval is a little bit difficult problem. So
Yep.
what's so special about Fourier phase retrieval problem compared to the generalized?
Good.
phase retrieval?
Yeah, that's a good question. So the generalized phase retrieval problem is really nice. First of all, at least the Gaussian version of it, or the version where your measurements are random. So in the generalized phase retrieval problem with Gaussian measurements, the only symmetry is the phase symmetry. And it kind of acts like a matrix problem. It has there's a kind of visually similar topology to the topology of matrix recovery problems. This is in some sense why it's not that surprising that we have good convex relaxations for generalized phase retrieval. So generalized phase retrieval is nice. I can even go back to the picture. And it's nice because the symmetry group is just a phase symmetry. Now, if I go to Fourier phase retrieval, all of a sudden the symmetry group is a lot richer. For Fourier phase retrieval, there are sort of shift and reversal symmetries, these extra discrete symmetries that correspond to the symmetries of the Fourier transform. And so because of that, the geometry of Fourier phase retrieval is very different from that of generalized phase retrieval. And empirically, Fourier phase retrieval is a much nastier problem. It's like harder to get methods that work well. And the methods that work well are a little bit more special, if I could say. They're a little bit stranger, at least to outside eyes. So that's an interesting problem. It sort of feels like to really, I mean, people do Fourier phase retrieval all the time, but it's a little bit finicky. There's some manual intervention needed, et cetera, et cetera. To really get something that's like solid in theory and practice, it sort of feels like one needs a combination of geometric intuitions and maybe a corresponding better formulation. This is just my outsider's perspective, having played with that problem a little bit. But I would say from the perspective of the talk, what makes Fourier phase retrieval much harder is that it has a much richer symmetry group.
Okay, great. Thank you.
Sure, sure.
Wonderful. So let's thank John again for the wonderful talk. And just so for the participants who remain, we will continue with the space webinar series every other Tuesday. So the next talk will be on October 20th, and that'll be by one of our organizers, Professor Bihan Van, and then we have space webinars continuing through the end of the year. So we hope to see you at the next seminar or one of the other ones this year. Bye.
All right. Thank you so much, everyone. Thank you, Sai. Thank you, organizers. And yeah, thank you.
Thank you, John.
All right. Take care, everyone.
Bye.